Hi, welcome to the video on improving model performance by pruning or hyperparameters tuning. By the end of this video, you will be able to explain the concept of pruning, perform pruning using hyperparameters of the decision tree. We closed the last topic with a cliffhanger on how to prevent a decision tree from overfitting. If you recall, we discussed that the decision tree is a non-parametric algorithm. Therefore, there are no parameters that we can control to prevent the decision tree from overfitting. But we also learned that the decision tree has some physical characteristics like leaf nodes, depth, etc. These physical characteristics are the factors that we can tune to prevent the tree from overfitting the data. As tuning these physical characteristics prevents the tree from growing and learning every single data point, this process is often referred to as pruning of the decision tree. We will first look at the physical characteristics of the decision tree that the sklearn allows us to prune. For this, we will simply create a new instance classifier of the DTC, which is nothing but the decision tree classifier of the sklearn library. Once we fit the model over the training set and run the cell, we can see all the list of tunable hyperparameters that the decision tree has. Now, there are quite a few parameters that we can adjust, but we will only be focusing on the most important ones. For the sake of simplicity, we are defining two functions that are calscore and effect, so that we will not have to manually change the parameters of the decision tree to observe the effect. We begin by defining the calscore. This function takes 5 parameters, that is model, which is obviously the decision tree classifier, x1 and y1, which represent the training set, x2 and y2, which represent the test set. In this function, we simply use the model.fit function and pass the training set to it. In the next line, we will predict the values for both the training set and the test set and then calculate the F1 score for both of them respectively. Lastly, we will return the F1 score of the training set and the test set. The next function we will define is called effect. It takes train score, test score, and x-axis and title as parameters. Train score represents the list of scores when predictions are made on the training set. Test score represents the list of scores when the predictions are made on the test set. X-axis represents the list of parameter values which were used to generate the respective F1 scores, which are on the y-axis, and title represents nothing but the title on the plot. The purpose of this function is to simply display the effect of the decision tree model for different values of parameters for the training set and the test set. Now that we have defined two helper functions to make a task easier, we will now look forward to the hyperparameters of the decision tree. The first parameter we will be looking at will be the max depth. If you recall, max depth of a decision tree was defined as the longest path between the root node and the leaf node. Using the max depth parameter, we can limit the depth we want in our decision tree classifier to grow. Our first task would be to gather the scores of the training set and the test set for different values of the max depth using a decision tree, and for that we will define a list called max depth and set its range between 1 to 50 so that we can observe the effect of this parameter value over a wider range. Once we declare a decision tree classifier with different max depth values, we will call the calscore function, which will return the score for both the training set and the test set, which we are appending at the end of previously defined empty list. Note that we are using a random state equal to 42 parameter. This ensures that results are reproducible. We can literally use any number. We need to make sure the number stays the same for reproducibility. We will simply call the effect function, which we had defined before. We will pass train scores, test scores, the range of parameters, and the title of the parameter into this function. When we run this cell, we can see the resultant graph as shown on the screen. In this graph, we can clearly see that as the max depth of the decision tree increases, the performance of the model over the training set increases significantly. But on the other hand, if the max depth value increases, the performance over the test score increases initially, but after a certain point starts to decrease rapidly. This is due to the fact that the tree starts to overfit the training set, therefore is not able to generalize over the unseen points in the test set. Among the parameters of decision tree, max depth parameter works on the macro level by greatly reducing the growth of the decision tree. Now the next hyperparameter that we will be looking at is the min sample split. It is a parameter which tells the decision tree what is the minimum required number of observations in any given node in order to split it. The default value of minimum sample split is assigned to 2. We can change this value as per our requirement. The value of 2 means that if any terminal code has more than 2 observations and is not a pure code, it can be split further into subnodes. Having a default value to 2 poses the issue that decision tree often keeps on splitting until the nodes are completely pure. As a result, the tree grows in size and therefore overfits the data. By increasing the value of the minimum sample split, we can reduce the number of splits that happen in the decision tree and therefore preventing it from overfitting. In this example, if we increase the number of min split value from 2 to 6, the resultant tree would look like this. Now we will observe the effects of minimum sample split on the churn dataset that we are working with. For this, we will use the same procedure which we followed during the max depth parameter. We will first declare a list of parameter values. Here, we will be using a range between 2 to 5000 with increments of 25. Now you might be wondering why we took this range and increment. Well, there is no particular reason except that we should be able to see the performance of a model over the wide range of parameter values. Just like last time, we run a loop for every parameter value and declare a different decision tree classifier. But this time, min sample split is changing with each iteration. Using the cal_score function, we will store the scores with respect to all the parameter values in the empty lists. The next step is to simply call the effect function and pass the respective parameter and observe the effect of the different parameter values over the decision tree. On running the code, we get the plot as shown on the screen. On increasing the value of the min sample split, we can clearly see that for the small value of parameters, there is a significant difference between the train score and the test scores. But as the value of parameter increases, the difference between the train score and the test score decreases. But we should also note that when the parameter value increases too much, there is an overall dip in both train score and test scores. This is due to the fact that the minimum requirement of splitting a node is so high that there are no significant splits observed. As a result, the tree starts to underfit. According to the data, what do you think is the range of parameter values for which we can say the tree is performing optimally?
The range is somewhere between 950 and 1000.
The decision tree has the optimal parameter value for minimum samples required to perform splits. We choose this region because the difference between the train score and the test score is in the acceptable range. Now, let's move on to another parameter called max leaf nodes. This parameter specifies the maximum number of leaf or terminal nodes. If after splitting we have more terminal nodes than the specified number of terminal nodes, it will stop the splitting and the tree will not grow further. Let's say we set the maximum terminal nodes as 2 in this case. As there is only one node, it will allow the tree to grow further. Now after the split, you can see that there are 2 nodes here and we have set the maximum terminal nodes as 2 and hence the tree will terminate here and will not grow further. This is how setting the maximum terminal nodes can also help us to prevent overfitting. But if the value of the max terminal nodes is very small, the tree is likely to underfit. Let's understand it better by plotting a performance parameter plot using the procedure as before. We can see that when the parameter value is very small, the tree is underfitting, and as the parameter value increases, the performance of the tree over both the test and the train increases. According to this plot, the tree starts to overfit as the parameter value goes beyond 25. Now, let's look at the last important parameter of the decision tree known as min sample leaf. This parameter specifies the minimum number of samples that should be present in the leaf node after splitting. This parameter again helps preventing overfitting as the parameter value increases. Let's understand it with an example. Let's say we have set the minimum samples for a terminal node as 5 in this case. And this is how the tree looks like after splits. Now here, the nodes marked with green color satisfy the condition as they have a minimum number of 5 samples, and hence they will be treated as leaf or terminal nodes. Here, the red node has only 3 samples, and hence it will not be considered as the leaf node, and its parent node will become the leaf node. And hence, this will be the final tree after setting the minimum samples for the terminal node as 5. So we have seen that we can control the growth of the tree by setting a minimum sample criterion for terminal nodes. If we plot the performance parameter value plot as before, we can clearly see that the model is clearly overfitting when the parameter value is very low, but the model performance quickly rises and rectifies the issue of overfitting. But when we keep on increasing the value of the parameters, the model slowly drifts towards the realm of underfitting. Now a good question to ask is, which parameter should we tune first and which parameter to tune last? As we mentioned before, the max depth parameter prevents trees from growing at a macro level. On the other hand, the rest of the 3 parameters tend to work on the macro level, allowing you to fine-tune the model at a very granular level. So a good practice is to start with the max depth parameter. Ideally look for the depth where the tree just starts to overfit the data. Once this depth is found, use the other 3 parameters to fine-tune the performance of the decision tree. Finally, you would want to choose a decision tree that generalizes well, that is, has a higher F1 score for test data, and the performance on train data and test data is similar. So that's it in this video. In the next video, we will discuss feature importance. See you then.